Now that we have proved some propositions about properties of partial limits, we arrive at this very important definition of the largest partial limit of the sequence and the smallest partial limit of the sequence, which are called the limit superior and the limit inferior, and they are denoted by Limsup and Liminf correspondingly. And it is in the generalized sense, meaning that the largest partial limit of the sequence could be positive infinity, and the smallest possible partial limit of the sequence could be negative infinity. So it's in the generalized sense, and at this stage it's not clear if the sequence has the largest partial limit and the smallest partial limit, and I'll explain what I mean by that. So we have seen examples of sequences which have finitely many partial limits, okay? And basically we've also proved a theorem that a sequence converges if and only if it has only one partial limit, which is the limit to which it converges. So basically, sequence having more than one partial limit cannot converge. So in the example of the sequence -1 to the power of n, it has two partial limits, +1 and -1. Basically, each of the values is being attained by the sequence infinitely many times. And so the limit superior in this case of the sequence -1 to the power of n would be 1, and the limit inferior would be -1. And at this stage, we've seen examples of sequences which have finitely many partial limits. And every finite set, we've also proved it, has the maximal element and the minimal element, which means that for sequences with finitely many partial limits, we can already deduce that they have, for them, the limit superior and the limit inferior always exist. Okay. But what about we don't know yet whether a sequence could have infinitely many partial limits. And then when you have an infinite set, it's not automatically guaranteed that it would have the largest element or the smallest element, right? Well, basically we'll attain the minimum and the maximum. And so, for example, if you look at the infinite set of all the real numbers from 0 to 1, where 0 and 1 are not included, then this set doesn't have the maximal element and doesn't have the smallest element, right? The minimal element and maximal element for this set do not exist. So we'll just have to see about that. And so let's see some examples. So basically, how many partial limits could a sequence have? So let's see an example. So we can see that in the case of this sequence actually has 3 partial limits, and it attains only 3 values, and each value is attained infinitely many times. So when n leaves remainder of 0 when divided by 3, basically here we would have a multiple of 2 pi, and so the sequence would be 0 for every n that is divisible by 3. When n leaves remainder of 1 when it is divided by 3, the value that the sequence is going to attain is square root of 3 over 2 times a. And when n leaves remainder of 2 when divided by 3, then the value of the sequence would be negative square root of 3 divided by 2. So in the case of this sequence, we know that it has only 3 partial limits. Basically, each such value is attained infinitely many times. And the limit superior of the sequence would be this. Suppose the a is positive, so then this is the limit superior and this is the limit inferior, and 0 is just an ordinary partial limit. Okay, so how about, can we construct a sequence that has any natural number of limits, like any finite number? And so this example can be modified to generalize for that as well. So we can define this sequence for, let's say that a is positive, and here m is natural, but so the natural numbers by definition, they do contain the 0, so I should have said m is not 0, because we're not allowed to divide by 0. So suppose that m is any natural number greater or equal to 1, then I claim that this sequence has exactly m partial limits. And so let's see how this sequence... So this is the sequence. So you can see the definition of the sequence an here. It's a sine of 2 pi over m times n. And basically here we plot the sequence. We look at the values of n, an for n from 1 to capital N, where n is capital M is limited to 10,000 because you can plot only finitely many elements of the sequence. So basically, you see here that for a of I don't know, let's take a any value, doesn't really matter. So for a7, okay, so this value here would be 7 square root of 3 divided by 2, etc. And then we've said, well, how the sequence would behave when we enlarge, take m to be larger. So it will be like the sine of a lower frequency, but we sample it at more points. So when we, so as you can see here, this sequence for m equals 3, those are the only 3 values that the sequence can attain, and they're attained infinitely many times. So let's see what happens when we enlarge m, take m larger and larger. Basically, when we see already this pattern of sampled sine wave being emergent here, right? So let's just take m bigger. Yeah, basically here you see the sine wave sampled at 53 points. Maybe let's take it sampled at 100 points. Okay, so what you can see here is that from the number of values here, from here up to here, we have exactly 100 numbers. And so each such value is attained infinitely many times. And there are hundreds of them, 100 of those values right here. So we have just taken those 100 samples, and basically that's how the sequence behaves. So we have constructed here a sequence with 100 partial limits, and it can be done to any natural number m. And what we can do here is to even generalize this example, not necessarily to a sine wave, but you can take any list of numbers and then arrange them periodically so that they are attained infinitely many times. We'll see more examples of that. And then you have a sequence with exactly m partial limits. Now that we have seen a way to construct a sequence with any natural number of limits, partial limits, the question that arises, can we have a sequence that has infinitely many partial limits? So this is the question we're about to answer. So how about countably many infinitely limits? Well, it turns out that it is possible to construct a sequence that has infinitely many limits, countably infinitely. And let's see how it's done. So we'll start the sequence with 1, and then from 1 we'll count 1, 2. And then we count again 1, 2, 3. And I hope that by now you get the principle behind the construction of the sequence. So it's going to be 1, 2, 3, 4, 1, 2, 3, 4, 5, and then on the nth step, so to say, we count from 1 to n, and then we count until 1 more, and we continue this process indefinitely. So the sequence that is being formed in this way attains every natural number infinitely many times, and therefore every natural number here, it's except for 0, is a partial limit of the sequence because it attains it infinitely many times. Therefore, we have constructed a sequence whose collection of partial limits is all the natural numbers except for 0, right? And this principle can actually be generalized to construct a sequence that has any collection countable infinity of real numbers as its collection of partial limits. And this is how it's done. So suppose we have a sequence alpha n of any collection of countably many, infinitely many real numbers. And then we will apply the same principle we've seen previously to construct a sequence such that all the elements of the sequence alpha n are partial limits of our sequence. And we're going to construct our sequence in the following way. So we'll start with alpha 1, and then we'll take alpha 1, alpha 2, etc. And then alpha 1 up to alpha n, and then we go add one element further. And then the sequence that is constructed in this way attains any alpha I infinitely many times. Therefore, each element of the sequence is a partial limit of this newly constructed sequence. So there we have it. for any collection of countable infinity of real numbers, we can construct a sequence such that those numbers are its partial limits. Okay, so the next question is, can we have a sequence that has infinitely many limits but an uncountable infinity, that is the continuum? And it turns out, maybe surprising, maybe pause the video to think about this, but if you want the answer, so the answer is yes. And so actually we know that the rational numbers are dense in the real numbers, which means that any interval that you take of real numbers would necessarily contain a rational number, right? And if you think about it, if you take any real number, you can construct a sequence. We've actually seen this, a sequence of rationals that converges to it. Basically, the nth element of this sequence would be the first n elements of the decimal expansions, like the first n digit of the decimal expansion in this infinite fraction of this real number, right? So it turns out, since the rational numbers are countable, then we can use Cantor's theorem to construct a bijection from the natural numbers to the rational numbers, and therefore all the rational numbers can be arranged into a sequence, right? So we can have the sequence an, which will coincide with the rationals. Now here's the point. Take any real number, right? Then any epsilon neighborhood of this real number will contain infinitely many rational numbers. And as a result, this real number would be a partial limit of the sequence of the rationals. This is the idea. So actually, if we look at the rational numbers as this sequence that we have constructed, or we can construct, then the collection of all the partial limits of the sequence is all the real numbers. And this is a deep idea that can be generalized to general spaces, and you can take any metric space which is not complete and construct a completion of this. Now, if it sounds unclear, then review the previous videos here. But anyway, I just want to give here some flavor of the more advanced topics. So the idea is the following one, right? So we've actually proved that any real number is a partial limit of the sequence, okay? And right. So this is the takeaway from here, that the collection of partial limits is this countable infinity of all the real numbers. And this shows that we can take the incomplete metric space of the rational numbers and construct a completion of it, right? So I'll just go over it briefly. If it's not clear, then you can skip it. It's a bit out of the scope of this course, but I just want to give you some flavor. So, try to get the idea. But if it's not clear at this stage, then, you can just skip it. Right, so basically what we can do is we can observe the collections of all the Cauchy sequences of rational numbers, right? Basically, you know that we review the lecture about the Cauchy sequences. Basically, you know that in real numbers, every sequence of real numbers converges only if it is a Cauchy sequence. And we could have Cauchy sequences that do not converge in the rational numbers, like the decimal expansion of the square root of 2, right? Any element of the sequence of rational numbers of the expansion of the first decimal expansion of the first n digits, right, would be converging to square root of 2, but square root of 2 is not a rational number. Therefore, Q is not complete. But we can look at this sequence of rational numbers that converges to square root of 2 as it is a Cauchy sequence. And actually we can define on all the Cauchy sequences. So there are uncountable infinity of Cauchy sequences in Q. So despite Q being countable, the collection of all the sequences of rational numbers is uncountable, clearly, and it's a very large collection. So what we're going to do, we are going to define an equivalence relation. So don't worry if it's not clear at this stage, but basically we say that two Cauchy sequences are the same if the difference between if their difference tends to 0. Now normally, if we knew that Q was complete, right? If Q were complete, that would mean that AN and BN converge to the same limit, right? Provided that those sequences or that they coincide, so to say. Because I mean, in the generalized case, those can converge. Like they can be identical and they can converge to infinity, but nevertheless means that if those are Cauchy sequences, then they have to converge and they have to converge to the same limit. So basically we say that two Cauchy sequences are the same if their difference converges to 0. Okay? And basically we can define the real numbers as those collections, as those equivalence classes of those Cauchy sequences. And this will be a way of completing the rational numbers, and actually one of the way to construct the real numbers. But this was just, to give you the flavor of the depths of the ideas here. And if it wasn't clear at this stage, then, just ignore it. Okay, so now we're going to discuss the idea of the existence of the limit superior and limit inferior, actually the largest partial limit and the smallest partial limit. So what we said previously, that if we have a sequence, right, we can look at the collection of all of its partial limits. And then if the set was finite, if we were to know that this collection of partial limits of the sequence is finite, right, then this would mean that every finite set has this maximal element, and then we could argue that for every sequence there exists the largest partial limit and the smallest partial limit, because you would have been able to take the largest element and the smallest element respectively of this finite set. But as we have seen, sequences can have infinitely many partial limits and even uncountable infinity of partial limits. So therefore, we need to show that actually the largest partial limit and the smallest partial limit exists. This is why it is not obvious. And here it exists in the generalized sense, which meaning that those limits could be infinite. But nevertheless, for every sequence, we can have the largest partial limit, if it is in the generalized sense positive infinity or negative infinity, could be infinite, and the smallest partial limit. And those are actually partial limits, meaning that we can find subsequences of this sequence that converge to this partial limit. Now, let us look at this theorem and what it actually says. It actually gives us a constructive way to find the largest partial limit and the smallest partial limit. So let us go over what this theorem states, and then we will see an intuitive example. Basically, to construct or to find the largest partial limit and the smallest partial limit correspondingly, what we will do, so the limsup of x is given as follows. So we take the supremum of the elements of the sequence starting from some n, which means that we discard the first n-1 elements. It's better demonstrated here. Let's look at this set. We discard the first n-1 elements. Then we take the supremum of this for every n. And then the supremum, we get actually a collection, an infinite collection of supremums, right? Because each time we discard another element of the sequence, so we get infinitely many supremums for the tails of the sequence. And then upon all those infinite collection of supremums, over them we take the infimum. And we claim that this is the largest partial limit. For the smallest partial limit, what we do is essentially the same in reverse. First, we take the infimum of the tail of all the tails, and then all the collection that we have obtained of those infimums of all the tails, we take the supremum, and this is the smallest partial limit. So now let's see how this behaves intuitively, and then we'll prove the theorem. To see the intuition behind what we've seen in the theorem of means to construct the largest partial limit of the sequence, let's observe the sequence xn, which is defined by as follows. This is cosine pi n pi over m. Basically, this is oscillating cosine. And here we multiply it by 1 plus, for the amplitude, 50 over n. So basically for n that goes to infinity, this amplitude would tend to 1 as n is getting very large, right? So it will tend to 1. And this cosine will be oscillating between this value and the minus of this. But the idea is that the largest partial limit would be 1. And so the idea to get closer to it would be to discard more and more elements of the sequence. And the more we discard, the upper bound of the tails is actually closer to the least upper bound, to the largest partial limit of the sequence. So let's plot the sequence and see how it behaves. Basically, this is this oscillating sequence. And so you see that each time the peak that we see, the local peak, is a bit larger than the next local peak. And then this would stabilize at the infinity at 1, so the limit supremum of the sequence is 1, right? But how to construct it? Well, basically the idea would be to go to this point, discard everything here, and then the supremum for the tails of the sequence starting from this point is this value, which is a bit larger than 1. And then the more we discard it, right, the more elements we discard, the closer the upper bound at this point would be to 1, right? So basically, none of those peaks is a partial limit of the sequence, but it is actually, if you take the collection of all those peaks and you take their infimum, this would be the largest partial limit. This is the intuition. Now let's see how this sequence behaves. So if we plot this function, then you see that this function is this envelope, upper envelope, and lower envelope for the sequence, right? Basically, when the cosine attains the value of 1, then this sequence would coincide with this envelope, right? And basically, the asymptote for this enveloping function is 1 and at infinity, right? Basically, okay, and then what else we can say about the sequence? So basically, we can take this point xk, x equals to k. Basically, we can, the idea here is that when x equals to k, we discard those elements that come before it, right? So maybe here we can erase the envelope function because we get the idea, right? We use the illustration of it. And then here, actually, we take the sequence where nxn, when n goes from 1 to n, and in Desmus, the values are limited to 10,000. So here we have kind of finite sequence. You have to extrapolate that this is infinite. So if I want to define the tails or the supremums of the sequence, I would be actually using the maximum. So here you see this value mk, which is the maximum of xn as n goes from k up to capital N. So the idea is m is the supremum of the mk is this supremum of the k's tail. Okay, so if we were to draw y equals mk here, right, then the value you would see that is here. But let's see. We'll add more and more elements here. So as we move k to, for example, 1, you see that the upper bound here, actually, there is an element of the sequence. This is the largest one in this case for n equals 1. And then this mk is this large value. We can see it. It's about 45.9. This is the upper bound for the whole sequence. But then as we discard more elements of the sequence, so basically the idea here is the sequence of mk's would be monotonically decreasing, and we will see it during the proof. Why? Because the more elements we discard, right, the less candidates we have for the supremum, right? So as k will go and become larger and larger, this supremum of the tail will be decreasing, as we see here, right? So it's going to be, if we look at this newly defined sequence mk, this sequence would be monotonically decreasing as k grows. Okay, we see here, and similarly, for the limit inferior, we could have this sequence mk of the minimum of, actually the infimum of those tails, right? So this would be y equals mk, and you can see how those values are getting adjusted And basically, the larger k is, the closer those become to 1 and to -1 respectively, which are the largest and the lowest, and the largest and the smallest partial limit of the sequence, right? This is the idea. What else can we demonstrate here? So one more thing. So y equals 1 and y equals -1 are the true partial limits, are the two largest and smallest partial limits. And then as we take k to be larger and larger here, I limit it to 200, but let's go over this demo once more. So this is the sequence. This is the largest partial limit. This is the limit supremum. This is the limit infimum. And then as we make k grow, right, those sequences mk, capital MK and lowercase mk actually converge to the largest and the smallest partial limits. So hopefully this gives you some intuition, and the proof will follow exactly the same steps. Basically, one more thing that I wanted to show you here is that I have defined, let's just undraw it, hopefully, is I have defined those values, we will see those sequences. So basically, the B sequence here, this is, we'll use it in the proof. So B1 is the maximum of all the elements of the sequence. B2 is the maximum of all the elements of the sequence starting for 2, etc. B3 is the maximum after we discard the first 2 elements of the sequence, etc. So I have made here some collection. And then you see that the sequence of B's, not B's, is monotonically decreasing, right? Because in each consecutive set is a subset of the previous set, right? So it can only have a smaller upper bound. Why? Because every upper bound for the superset would be also the upper bound for the subset, okay? And similarly, we have the sequence, the A sequence of A's, and this will be monotonically increasing. Why? Because we discard elements, so there are less candidates for the smallest element, so every lower bound for the superset will also be a lower bound to the subset. And then if we were to plot those, so here we have collections of all the B's. This is, you can see this is monotonically decreasing. This is B1 and B2 and etc. And you can see that they monotonically decrease, and they actually coincide with those MKs that we have had previously. And then here would be the collection of the A's, just ignore the C here, which will be monotonically increasing. So if we now draw the entire sequence once again, hopefully it's not going to be too cluttered. This is the sequence. Okay, nah, it's too cluttered. But the point, the main takeaway here is that you see for k equals 1, it coincides with this B1. And then for k equal 2, you would see that, okay, let me just adjust it. For k equals 2, it coincides with this B2, right, this MK. It's essentially the same, right? And then, as you see, those lines are going to tend to 1, which is the limit supremum, and those would tend to -1, which is the limit infimum. Maybe it made more mess than intended here. So let me undraw those sequences. The reason for demonstrating those sequences here is because we're going to use them in the proof, okay? But the main takeaway here is that, okay, this is the limit supremum, this is the limit inferior, and then we discard elements as we move k, right, and make it larger. We discard elements of the sequence. We'll look at the k's tail, and we'll look at the least upper bound and least lower bound, and the largest lower bound. And then as we discard more and more elements, those will be converging to the limit supremum and limit infimum correspondingly. So hopefully it was clear enough, and now we'll start the proof. So now that we have seen the intuition behind this, what is claiming this theorem, let's actually prove it. And so one more thing to add here, whenever the sequence xn is unbounded above, then of course the limit superior is going to be positive infinity, and the limit inferior when the sequence is unbounded below is going to be negative infinity, and whenever the sequence is bounded, then those are going to be real numbers, right? Okay, so as we've seen, we begin the proofs, and as we've seen, the key step here would be to observe those sets of tails. Basically, we take the sequence and we discard the first -1 elements. Now, let's handle first the case where the sequence is unbounded above. So if the sequence is unbounded above, then for every n, the supremum of this set is going to be infinite. And why is that? Basically, we need to show that there is no upper bound for the set of the sequence whenever we discard any finitely many elements. So the assumption is that the sequence is unbounded above. And then when we discard finitely many elements, the sequence will remain unbounded above. And why is that? Because suppose that we've discarded finitely many elements, then every finite set has a maximal element and a minimal element. And therefore, if we were to assume for contradiction that the remaining set is bounded, then there is some number that is an upper bound for the remaining set, and then there is the maximal element of the elements that has been discarded. And then the maximum between those two would be a bound for the entire sequence. And this would be a contradiction because we assumed that the sequence is not bounded above. So hopefully it was clear enough. We've already made several such arguments, right? And so basically here, for every such n, every tail, if the sequence is unbounded above, every tail of the sequence would be unbounded above. Therefore, for every n, the supremum of the set is going to be positive infinity, right? And similarly, if the sequence is unbounded below, then the infimum of this set would be negative infinity. And therefore, if we denote, we've denoted this by xn, each such xn is, if each such xn is unbounded above, if the sequence is unbounded above, then each such xn is unbounded above, right? And then basically what we're going to do, we're going to construct a subsequence of our sequence that will converge to infinity. And this is a fairly standard argument that we've already invoked, but for purposes of completeness, I'm bringing it once again. So since x1 is unbounded, then we can choose an element in the set, which will be greater than 1. And why is that? Because 1 is not an upper bound for the set x1, because it's unbounded above, right? Okay, and then the set x2 is unbounded above. And so 2 is not an upper bound for the set x2, and therefore there are infinitely many elements in x2 that are greater than 2, right? Because the set is unbounded above. And therefore we can find an index in 2, since there are infinitely many of them, that would be greater than 1, such that x and 2 will be greater than 2. And then when we continue this construction in xk plus 1, we'll choose an index for x plus 1, we'll choose an index nk plus 1, such that x nk plus 1 is going to be greater than k plus 1, and nk plus 1 is going to be bigger than all the indices selected before it. And in this way, we have constructed a subsequence of the original sequence such that x and k is greater than k for every k, and therefore by the generalized limit arithmetic theorem, this limit is going to be infinite, and therefore we have shown that there is a subsequence which converges to infinity, therefore the limit superior of the sequence is infinity when it's not bounded above. Okay, and so the case for the sequence which is unbounded from below is similar, right? So now let's assume that the sequence xn is bounded. This is the interesting part. So whenever it is bounded, if we look, we now define the sequence bn that you've seen in the visualization, which would be the supremum of the tails, or the supremum of the set xn. It's actually a sequence of sets, right? xn. And similarly, we defined an, which will be the infimum of the tails. And now the assumption is that the sequence xn is bounded, right? This sequence is bounded above and bounded from below. So now, since it is bounded, we can invoke the axiom of completeness and this set here would be bounded. And therefore, since it is bounded, the axiom of completeness states that for every bounded set there exists a supermum that is the least upper bound. And Bn is defined in exactly this way. Similarly, this set is bounded from below, and therefore axiom of completeness once again implies it is equivalent, that this set, every set bounded from below, will have an infimum, or the largest lower bound. And therefore, those sequences are now well defined due to the axiom of completeness, because those sets are bounded and the supermum and the infimum exist accordingly, right? Okay. Now, one more thing to notice here, it's a crucial step, that since at every step we discard more elements, then this set xn plus 1, as we've seen in the visualization, is contained in the set xn. And therefore, it would imply that the sequence Bn is monotonically decreasing. Why is that? Because the supermum of xn has to be at least as big as the supermum for xn plus 1. Why is that? Because in xn we have more elements, therefore, so to say, intuitively more candidates for the supermum. But if you want to make this argument rigorous, then every upper bound for xn, which is the superset, is also an upper bound for the subset xn plus 1, and therefore the least upper bound for xn is at least as big as the least upper bound for xn plus 1. Therefore, this sequence of bn's is monotonically decreasing. And remember that b1 also exists in this case, and it's a real number. Why is that? Because we've assumed that the entire set of the sequence, which is x1, right, is now bounded, and therefore for this bounded set there exists a supermum which is a real number due to the axiom of completeness. I may be repeating myself, but this is for clarity, right? So now the sequence Bn is monotonically decreasing, and it's actually bounded above by b1, which we have proved that this element is actually a real number and it exists. And therefore Bn would be a monotonically decreasing sequence. Yeah, we'll need to show that it's actually bounded from below. It's bounded from above, but it's also, we'll see that it's also bounded from above. From above and below. Now, what about an? So for an, the argument is similar. So an as a sequence is going to be monotonically increasing. And why is that? Because in xn, so to say, there are more candidates for the smallest, so to say, possible elements. Now, of course, to make it rigorous, we will say that since xn is the superset, then every lower bound for xn is also a lower bound for xn plus 1, right? Because there are less elements in xn plus 1, okay? And so the sequence an would be monotonically increasing, okay? And this is just what I said intuitively. So just remember this intuition. This statement, of course, is not rigorous, but this is something that you could hold in the back of your mind for intuition of why this works. And whenever you need to be rigorous, then invoke the argument that I just said. Okay, and what we also have is that for every n, an is smaller than bn, right? Because just due to the definition, bn is the upper bound for xn, and an is the lower bound, right? bn is the least upper bound, and an is the largest lower bound. So, of course, bn is greater than an. And now the important thing is that since a1 exists, why a1 exists? a1 exists because the set x1 is assumed to be bounded. And so due to the axiom of completeness, its infimum exists. And its infimum is by definition a1. So a1 is a well-defined real number. And then a1, since the sequence an is monotonically increasing, and every an is smaller or equal than any bn, then actually a1 is a lower bound for the sequence bn. So now the sequence bn is monotonically decreasing, and it's bounded from below by a1. And then monotone convergence theorem comes to the rescue. So the sequence Bn is monotonically decreasing, and it's bounded from below by a1, by a real number. Therefore, by monotone convergence theorem, the sequence B1 converges. Okay. Yeah, so this is what I just said, and similar argument shows that the sequence AN is monotonically increasing, and B1 that exists is actually B1 is an upper bound for the entire sequence AN. Therefore, this sequence AN is monotonically increasing and bounded above, and therefore, due to the monotone convergence theorem, the sequence AN also converges, right? Okay. Right. And yeah, the monotone, so if we have a monotone decreasing sequence, right, which is bounded below, then it would converge to its infimum. And if we have monotonically increasing sequence, which is bounded above, it will converge to its supermum. Okay. So now what we have is that since the sequence Bn converges, we will define by B its limit. So its limit exists and it's a real number. And then since a monotone sequence, which is decreasing and bounded from below, converges to its infimum, so B is the infimum of those Bn's, right? But the Bn's were defined as the supermum of those sets Xn. Okay. And so now this B, the limit of this sequence Bn, is exactly this expression that we've seen in the theorem. It's the infimum over K of the supermums of all the possible tails. And similarly for the sequence An, which is monotonically increasing and bounded above, it converges. It has a limit. And its limit is actually the supermum of the sequence. Okay. And so, but An was itself defined as the infimum of Xn, and then we get the second expression as in the theorem. Okay. It remains to show that A and B are actually the largest and the smallest partial limits correspondingly. Okay, and that's exactly what we're going to do. Okay, so the first step would be to construct a subsequence of Xn that would converge to A and B. And this will show that indeed A and B are partial limits. And then we'll show that for B, that for any partial limit that we have for the sequence, it has to be less or equal than B. Okay, so let's proceed. So first of all, for each n, by the definition of Bn is the supermum of the set of tails. And so it's the supermum, more explicitly, of this tail. Okay. And so now we're going to invoke the definition of the supermum, and actually say that if we take Bn, Bn as the supermum of this set, then if we make it ever so slightly smaller, no matter how smaller we take it, it is no longer an upper bound for this set. Why is that? Because the supermum is the least upper bound, so therefore you cannot make it smaller and still have it as an upper bound, because it wouldn't be the smallest upper bound, of course. So basically, for Bn, consider Bn minus 1 over n. This means that this number is no longer an upper bound for the set, meaning that we can find an index here, and we denote it by Kn. So this K is a function of n, okay? So it depends on the value of n, such that x with this index will be bigger than that, right? Because this is no longer an upper bound for the set, therefore there is an element in the set which would be bigger than this number. But on the other hand, Bn is the supermum for this set, and therefore it's bigger than every element in the set. Okay, so now we have a way of defining a sequence of indices such that for every n, this inequality is satisfied. Now the only problem here, we want to construct a subsequence, as you see, of Xn, but the way it is defined here, this sequence of indices is not necessarily strictly increasing, right? Because, well, what can happen is those indices could be like the same index or index getting fixed so to say. So, for example, if for here this index would be, for example, n plus 100, right, for 1 over n, and then once you take n ever so smaller, you get stuck on the same element. So now we're about to resolve this minor technicality that the sequence is not necessarily increasing. So first of all, what we show that we have an infinite sequence kn of indices such that this inequality is satisfied for every such index. The only problem, this sequence might not be strictly increasing. Now, what we also have is, by construction, every kn has to be at least n. And why is that? Because if we look at this set, right, the indices start from n. So each element of the set which would satisfy this, right, this inequality, since Bn is the supremum of that, it has to have an index of at least n. So the sequence kn that we selected here is greater or equal than n for every n. And this implies that this sequence of kn, while it may not be strictly monotonically increasing, still is bigger than a sequence that converges to infinity. And therefore the limit of the kns as n goes to infinity is infinite limit, right, is infinity. And now we can use this property, basically, now we can use this to construct a subsequence of the kns which would be strictly increasing, right? And basically, how would we do it? Well, basically we can take the first kn, right, first index, and then since this sequence is increasing to infinity, there's an element in the sequence that will be greater than k and 1. And so we take index k we choose any index such that, and 2, such that k with this index is going to be greater than k with the index and 1. And we continue this way, and this way, so the next step would be to find an index that is greater than this, right? An index n 3 such that k with the index n 3 is strictly bigger than k with the index n 2. And this way, we define a subsequence of kn that would be strictly increasing. So this n is a function of L, so to say, because you start with k with the index n1, right, for the first one, and then you want to find an index that will be greater than k with the index n1. So the k with the next index is greater than k with the previous index. So you have here a sequence of indices. You have index n1 and n2 and an L, so to say. So this is kind of the trickiest part here, that you have a subsequence of a subsequence. So this is the sequence which runs over the values of L, but basically for the sequence kn, we have selected a subsequence of indices that is going to be strictly increasing, right? And then you have this subsequence of xn that we wanted to construct originally, and this is a proper subsequence because those indices are strictly increasing. So now if we consider this subsequence, so know that by the construction, so looking at here, so if the sequence x has the index kn, then this inequality is satisfied. Therefore, if this for this sequence we have the index nl here, then by this construction, which holds for every n, we have to have that b with the index nl minus 1 over nl is smaller than k with the index nl, and on the other hand, by the definition of the sequence of b's being the supremum of that, it has to be smaller than that. So now we have a proper subsequence of xn, right? And now we can invoke the limit arithmetic theorem together with the sandwich theorem. So to conclude that this subsequence is now converges to b, which proves that b is indeed a partial limit of our original sequence. So this is making progress already, right? And now, so just to justify what I said previously, so the sequence of nls has to go to infinity, obviously. It just goes to infinity because it's strictly increasing. And then b with the index nl is, okay, so if we take this limit, right, so since the sequence Bn converges to B, then every subsequence of, okay, let's look at the sequence Bn, right? So this sequence Bn, we've proved that it converges to B, so every subsequence of Bn has to converge to B as well. So now the limit of Bnl converges to B, and 1, so NL converges to infinity, therefore 1 over NL converges to 0, therefore this limit exists and equal to B. Okay. So now we're going to prove that Bn has to be the largest partial limit, and for that we need to consider any partial limit. And then for any partial limit, what we'll show it has to be smaller or equal to B. Okay, and let's see how it's done. So consider any subsequence of x that would converge to a partial limit, call it x. And x is just any partial limit of the sequence xn, and since x is the partial limit of the sequence xn, there is a subsequence of xn that converges to x. Okay, and now we can consider the subsequence b with the same indices, right? So it would be the corresponding subsequence of b, okay? Of a sequence bn, okay? So now, since the sequence bn converges to b, then any subsequence of this sequence has to converge to b, right? But then, so what we have is that since b and k is the supremum of this tail by definition, so being the supremum, b and k has to be bigger or equal to x and k, okay? So x and k is small or equal to b, and now since both the sequences are convergent, we can apply the limit arithmetic theorem, the generalized limit arithmetic theorem for inequality, to conclude that the limit of this sequence has to be smaller or equal than the limit of this sequence. But since we know that the sequence of bn converges to b, then the limit of this sequence has to be less or smaller than b, right? So basically what we have is that the limit of x and k has to be smaller than this limit, and then since the sequence b of bn's converges to b, every subsequence converges to b, and so this is b, but we have showed that b is by definition is this limit superior. It was the expression in, and so b was defined by an expression in the theorem, and then it turns out that this is b is indeed a partial limit, and every other partial limit is smaller or equal than b, therefore bn is indeed this limit superior of xn, so b is the largest partial limit. And that concludes the proof of the theorem because of the way bn is defined in the theorem. So we've proved it. And the case for the Liminf is analogous, right? So I would leave it as an exercise. Okay, so now let's prove another theorem. So suppose that we have an as a bounded sequence, then an converges if and only if its limit superior equals to its limit inferior, and this is quite a natural thing to ponder about, right? This statement seems very natural. Why is that? Because one direction of the proof is very easy, because if the sequence n converges, then every subsequence of an has to converge to the same limit, and therefore an has only one partial limit, so the largest partial limit and the smallest partial limit are actually the limits of the only limit of the sequence, and therefore they are equal. So the Limsup equals the Liminf, and this is the only limit of the sequence. Okay, and it's a converse that is a bit less straightforward, but still quite straightforward. So suppose that n converges, then as we said, every subsequence has to converge to the same limit. Therefore, this implies that the limit superior and the limit inferior are this partial limit, and they're the same, right? Because the collection of all the partial limits contains only one element, which is the limit of the sequence, and therefore it's the limit superior and limit inferior at the same time. Okay, conversely, now suppose that we have this equality of the limit superior and the limit inferior, then we have to show that an converges. And basically what we're going to do is we're going to show that every subsequence of n has to converge to the same limit, right? So since we assume that an is bounded, right, then the Bolzano-Weierstrass just implies that it has at least one partial limit, right? Because the Bolzano-Weierstrass theorem says that for every bounded sequence there is a convergent subsequence. Okay, and now it has at least one partial limit, so now for any subsequence, if I was a partial limit, any partial limit that we have, then by the property of the Limsup and Liminf, L has to be greater or equal than the Liminf and smaller or equal than the Limsup. But then Limsup, by assumption, is equal to the Liminf, right? We have this inequality, which implies that L has to be equal to both of those numbers. Therefore, every subsequence of n has to converge to the same limit, which means that we can consider the sequence an as this trivial subsequence of itself, and therefore it has to converge to L, right? And that concludes